So here we are on the next page of section 2.5, and this is continuing with our previous example. And just a reminder, just in case you had forgotten, we're taking a look at that system of differential equations that we know is completely decoupled. We actually know what the general solution is, and we've proven that this is a particular solution. But we're going to kind of set that aside and say, for our system of differential equations, we're going to use Euler's method. And you'll notice there's some information given right away in the problem. The step size is given as delta t of 0.05. And we want to approximate the solution and check how close the approximate solution is to the real solution, the one that we know from the previous page, when t equals 2, t equals 4, and t equals 6. So notice this is giving us kind of three different predictions. So we're predicting at three different places. So these are our t-value checkpoints, if you want to think of it that way. And this is where we're going to estimate the solution curve location. So the whole point of Euler's method is that you start at a known value and you move forward from there. So we need to have some initial value, which is given to us right here. So remember, this initial condition written in matrix form can be decoded, and this is the initial condition that yields the particular solution that we're going to want to play around with. But this is also the initial condition that yields the particular solution that we just verified. Because if we start off when t equals 0 at an x value of 1 and a y value of 3, that leads to this solution right here. Right, a quick check and you can see that that works out. So we're actually kind of starting with the initial condition that should produce the particular solution that we already verified. So what we're going to do now is find out what happens when we come up with some predictions. And so we're going to predict for specific values of t what happens for x of t and what happens for y of t. So we know that we have to predict, well, it's not much of a prediction. We know the value of x and y when t is 0. That's our initial condition right there. So I probably should draw attention to that. So I'll say that our initial condition right there is this right here. So that's where we're starting off with our initial condition. So the real question is, what happens when t equals 2 or 4 or 6? What about the x and the y? What does our Euler's method predict? And how does that compare to the actual location? So these are going to be predicted values. And we'll leave a little bit of space down here to be able to fill in the actual values. But we won't do that right now. We'll figure that out here in a second. So what we need to do is come up with a way to tell Maple to actually do that coding for us. So I'm going to switch over to Maple, and you'll see that I've actually done a little bit of work in the background. This is all basically the stuff that we know to begin with. We know that the general solution for our system looks like this. We showed that on the paper. And so that means that our particular solution with our initial conditions gives us a particular solution, and that's the one that we're trying to approximate. And because we're trying to approximate, it might be nice to see what does it look like on the phase plane. And so for an initial condition of when t equals 0, y or x equals 1 and y equals 3, that starts off right there. And so our Maple's kind of high quality solution predicts the curve is going to look like this. The only question is, what will Euler's method do when we ask it to predict the location when t equals 1, 2, 4, 6, any value of t. This is how far it goes when t equals 1. That's what we're verifying here. So in 1 unit of time, it actually travels quite a distance on the phase plane. So you'll notice down here, what was I going to say? Oh, I'm getting distracted by my own typing here. So we know that we know what the solution curve looks like, and so now we're going to try to figure out what about Euler's method. And so the code for this, I'm going to just paste it in here. The code for this looks kind of familiar. As a matter of fact, it's sort of disarming that you would see this and think, is that really Euler's method? It's just a D-solve. But notice, we're solving our system of equations. I'd name them up above, equation 1, equation 2, with my initial condition. That's the first thing in my D-solve. And then the second thing in my D-solve is I'm identifying the dependent variables, x of t and y of t. And then this is where the code really gets specific. I'm telling Maple I don't want just any old solution. I want a numeric solution. And then the next thing that I tell it is I want the particular method used to be what's called classical method. Now, classical is Euler's method, so that's exactly what we mean when we say the method is classical. And then the next thing is the output, and you'll notice I want to output, oops, I didn't want it to go all that far. I want an output to be an array. And you'll notice the values for the array should look familiar. Those are the values for t. 0, 2, 4, and 6. Those are the values that I want. And then the step size, and Maple of course knows the step size is going to be my independent variable, and the step size is 0.5. So let's see what kind of output we get when we hit enter on this. Okay, we hit enter, and this is what we get. Notice at the top there's like a title, or there's a legend for this table, and that's telling us the first column is a value of t, the second column is a value of x of t, and then the third column is a value of y of t. And so notice that first row looks exactly what's on my page right here, 0, 1, 3. And now what I'm going to be able to do is fill in these other values using the table that Maple gave us. So I'm going to go ahead and fill in those values and then switch over to the other screen. You go ahead and do the same. Okay, now that I've filled in my x of t and y of t values, remember that this table is what we predict the solution is going to look like using Euler's method. But the good news is we actually have the correct solution. And the 100% particular solution for this initial condition. So we know the correct solution is x of t equals e to the 2t and y of t equals 3e to the t. Now you might look at this and go, okay, well that's the right answer. Will it predict the exact same values, or will they be close? Well, let's find out. So let's see what they're going to predict for the same t values. What does it predict for x of t and y of t? So remember 0, 2, 4, and 6. And so our first row is going to look exactly the same because that's our initial condition. But our second row, for the x value, it's going to be e to the 4th power. So e to the 2 times 2. E to the 4th power is roughly 54.6. We can grab a calculator and come up with that. And 3 times e to the 2 is roughly 22.167. Now, take a look. We guessed 16 and almost 16. This is 54, almost 55, and 22. So already, after 4 steps, because we've gone 2 units of time and our step size is 0.5, after 4 steps, we're already quite a ways off. So these values through here are going to be our actual location of the solution curve. So we know after 4 steps we're quite a ways off. But let's see what happens with the others. Take a second and do the calculations for t equals 4 and t equals 6. And you could just use a calculator to come up with decimal equivalents. So take a second and do that. I'm going to write mine in as well. So after running those calculations, we find that our solution, our actual solution for x, is way, way off compared to our prediction. And our predicted y values are nowhere near the predicted y values. And remember, we're taking step size of 0.5 in the t direction. So this is after 4 steps. That's after 8 steps. This is after 12 steps. So after 12 steps, we are really, really, really wrong. So what does that tell us? What's going on? Well, I mean, from our experience with Euler's method before, if the step size is too big, then your predictions are going to be pretty crappy. So let's use a smaller step size. So let's rerun our Maple code for a smaller step size. Let's try 0.1 for the step size. Now this is basically increasing the number of steps by a factor of 5. So what does that mean then? Well, let's hop on Maple and find out. So in Maple, we can just copy and paste that code if we want to. And then all we have to do is change the step size, because everything else is going to remain the same. So I'm going to decrease the step size, thus increase the number of steps. And notice the output still stays within a table. And you can tell by looking at our values that our output values for x and y are now much bigger at each one of these points in time. And that means we're getting closer to being a good prediction. But it's still not great compared to our actual answer. So let me go back to the notes and we'll write this down. So seeing our results for this smaller step size, you can see that we're getting closer to the right answer, but we're still a long ways away. At t equals 6, we're still a long ways away from being correct for x and y. So what does that mean? Well, approximated values for smaller step size are going to be more accurate. But there comes at a cost. So we like to think of this as being a good thing because smaller step size leads to better accuracy. So we're happy about that. But it also leads to more error accumulation. And that's not good. More error accumulation because each step we're picking up a little bit of error along the way. And that means that shows up in terms of our decimal place. How far out do you round? You'll notice I just rounded to the nearest whole number. I'm not even close enough to worry about decimal places. But the other problem with this is it's more computations. And the complexity of the computations is higher. So that means for our purposes, I can go into Maple and say, let's try it again, but with a really, really small number of or step size. So if I switch back over and I try it again and I copy this down and I say step size of 0.0001, now that means there's an awful lot of steps. So watch what happens when I hit enter. Notice it says the following errors occurred. I couldn't evaluate the solution past this point, 0.4 or 4.999 for t value, because max fun limit exceeded, which always cracks me up whenever I read that. I always think there's a maximum amount of fun you can have. No, it's not maximum amount of fun. It's literally I've run out of the numerals that it can store. So it's not able to store enough decimal places to detect a difference between this step and the next step. So notice it was able to do the first couple, and that's actually pretty good. 54 is pretty good for our first step for 2, and then 2978 for the next one. that's actually really good. The right answer is 2980. So that's really good. That means that we're quite accurate after after t equals 4. The problem is getting Maple to go beyond that means that we have to have enough storage room to be able to store all those decimal places to note the difference between them. And Maple just runs out of storage space. If I back this up one decimal place on the step size, I can actually get predictions that are not bad. 54.3, 54.6 is the right answer. 2957, 2980 is the right answer at that one. And this is 160,816. The actual answer is 162,754. So that's actually really good. But notice, we pay the price. The complexity of our calculations step up. So the last little bit on this page is a question about kind of concept. How and why do the Euler approximations differ from the solution? So let's think about the how first, and I'm going to go down here with that. How do the Euler approximations differ from the solution? Well, we're approximating the curve location, the x and y coordinates, right? So we're not actually following the curve. So we're approximating the curve location, but we're not actually following the solution curve. So as soon as we get off by a little bit after the first couple of steps, then forever we're going to be off. We're never going to be able to get back onto the solution. So how do they differ? Well, they differ because we're approximating from the get-go. The very first step that we take is an approximation. And then, of course, the second part of this question is, why do they differ? Why is there so much difference? Well, the why is a little bit easier to understand. Each step takes us further away. From the actual answer, from the actual curve. So unfortunately, no matter what we do, we're always going to be approximating, and it's always going to be not great. But you've seen that if you take small enough step sizes, you can do a pretty good job of approximating until things get just too complicated. And so I do want to add one more little note, just as a callback to our experiences in Chapter 1. If you use the second derivative test, you can determine the concavity, just like we did in Chapter 1, and that tells us what type of error to expect. And that could be an over or an under approximation. What type of error to expect in our estimates. Now, it is worth noting that that means we're going to be looking at the second derivative test for both the x and the y. And if you remember, the second derivative test for this guy right here, if that's the actual solution, the second derivative is going to be positive. And so is this one. So we're looking at a situation where both for x and y, we've got a concave up situation. This thing is going to be for x and y growing super fast. So we're always going to be approximating under. That's why no matter how good no matter how small our step size was, our actual answers were always smaller than the actual, our predicted answers were always smaller than the actual answers. So that gets us to the end of this example. We've got another example on the next page where we're going to practice this one more time, and then we'll be done with Chapter 2.